Hey everyone, looking at class number 42, our goal is to use Newton's first law to explain centrifugal force. Notice how I have centrifugal force in quotes there because the centrifugal force isn't actually a force, it's just a feeling. We'll talk about that today in class. And it says to calculate the tangential velocity, centripetal acceleration, and centripetal force. So make sure you check out that video and think of why that happens. So A says here, all right, you're in a car and it makes a sharp left turn. Which way do you feel your body go? You feel your body go to the right. Your car makes a sharp right turn. Which way do you feel your body go? You feel yourself go to the left. So what's the agent of this force that pulls you? What's the cause of the centripetal force in this case? There actually is no force. What you're feeling is actually your inertia, your body's tendency to want to go in a straight line to resist the change in speed or direction. This is the centrifugal force. So the reason we put it in quotes all the time is because the centrifugal force is not a force at all, it's a feeling. What keeps you moving in the circle is the centripetal force. For example, when you're in the car and it's turning, you make a right-hand turn, you feel your body go to the left. All right. The centrifugal force is that feeling of you going to the left, though it's really just your inertia trying to carry you in a straight line. The centripetal force that keeps your body moving in the circle is applied by the friction between you and the car seat, the force of the car door pushing against you that keeps you moving in that circular path. And he says, if a car traveling in a straight line suddenly makes a turn, which way does your body want to keep going? How can Newton's first law explain this? So it wants to keep going in a straight line. Objects move in straight lines unless acted upon by a net force. So look at this image here. This does a pretty good job of showing it. You see this car here, it wants to go in a straight line. As it turns, it's turning left. The passenger wants to keep moving in a straight line path. That straight line is to the right of the path the car is actually traveling. All right, so as the glass of water goes in a circular path, which way does the water want to go? What is preventing it from going that way? Mention Newton's first law in your explanation. So if you look here, now there's a few different ways to describe this. We have the cup going around in a circle, and here it's upside down. The water wants to go at any given point in a straight line tangent to the circle. It wants to leave the circle. Picture if you poke holes in the cup, the water's going to fling out in all directions as you spin it around. So what's preventing it? The cup is what prevents the water from leaving the circle. Okay, so the reason the water stays in the cup is because the water always wants to go in a straight line tangent to the circle. The walls of the cup are what prevent it from leaving that circle. So as long as the cup keeps going around in a circle, the water will be forced to stay in that circle. So here are circular motion equations that we can find on our reference table. The first one is Fc equals mac, that means centripetal force equals mass times centripetal acceleration. Centripetal force is in newtons, mass has to be in kilograms, and centripetal acceleration has to be meters per second squared. We also have an equation that centripetal acceleration equals speed squared divided by r in meters per second and meters, respectively. Now, we frequently put those two equations together to get another centripetal force equation, where we substitute v squared over r into centripetal acceleration, and we get this equation mv squared over r. So I will frequently write that in this course, though it does not appear in the reference table. Is simply these two equations put together. Substitute v squared over r into AC, you get mv squared divided by r. So here are some sample questions. We have a 1,500 kilogram car traveling around a curve with a radius of 45 meters. The centripetal acceleration of the car has a constant magnitude of 3.2 meters per second squared. Calculate the speed of the car. So if AC equals v squared over r, 3.2 equals v squared over 45, cross multiply, take the square root, we get 12 meters per second. To get the centripetal force, we just have to multiply centripetal acceleration, which we are given, times mass, which is 1,500, and we get 4,800 newtons. So it says here, what force provides the centripetal force needed for the car to travel around the curve? It's friction. Think about it. If friction were to disappear, this thing would, fling off off to the side if there were ice or something. D says determine the speed, determine what happens to the magnitude of the centripetal force of the car as it travels around the curve if the speed of the car decreases. So here's our big centripetal force equation with all the variables in it. If V goes down, centripetal force goes down, okay, because they're both in the numerator. What about the radius? If the radius decreases, well, this is an inverse relationship. If R gets smaller, centripetal force has to get bigger, meaning the amount of friction required would increase.